Hello everyone. Today we'll understand the concepts of bias and variance. Imagine we run an ice cream business and we want to know the relationship between the temperature, the ambient temperature, and the sales of ice creams. Okay. Let's say X is the temperature and Y is the sales in 1000 rupees per day. Let's fit a simple model that is simple linear regression. We try to fit that model on 3 different weeks. That means we'll note down the temperature and the sales data for all the days on week 1, then again on week 2 and again on week 3. Then based completely on the data of week 1, we'll try to create a linear regression model. Let's call that model 1. Then based on the data from week 2, we'll again try to create another linear regression model. Let's call it model 2. And from all the data that we have of the temperature and the sales from week 3, we'll create a third different model, which is third linear regression model. We'll call it model 3. Okay. Now, assume that we are testing it on the fourth week. Let's say we are testing it. And for one particular temperature, let's say X equal to 33, we find the prediction of sales as per the model fitted on week 1 to be 8.9 thousand, that is 8,900 rupees. Okay, if we use the model based on the data of week 2, the predicted sales are 8,100 rupees. And if you use the model based on the data from week 3, the prediction is 8.6 thousand or 8,600 rupees. But in reality, we find that the actual value is 7.2K, that is 7,200. Okay. So, firstly, let's try to find out what is bias. Okay. Now, for that, let's establish some notation first. X is the independent variable, that is the temperature. Y is the dependent variable, that is the ice cream sales. Now, y equal to fx is the true relation, which we don't know. Y hat is equal to f hat x. Here, f hat is the predicted function or the predicted relation. Okay. And y hat is when you actually plug in the x values in that predicted relation. So, y hat is the predicted value. Okay. Now, bias is given by, first we try to find the average of all the predicted values. For that, the operator we use is the E, the expected value operator E. Okay. So when we can find E of f hat x, we get the average or mean of all the predicted values, which comes out to be 8.53. From that, we subtract the actual value that is observed. Okay. Fx, the value fx. So the fx value is 7.2. So 8.53 minus 7.2, which is 1.33. This is the bias. Next, let's go to the concept of variance. Now here, let's take a look at the predicted values again, 8.9, 8.1, 8.6. How much do these values vary? Okay, so we trained the model based on the data from week 1. We trained another model based on the data from week 2. And we trained a third model based on the data of week 3. How much do the predicted values by these 3 models vary? Okay, so that is the variance. So first we have to find the mean of all these values. So E of f hat x. Then from every data point subtract the mean. So f hat x minus E of f hat x. Okay. Then we square it to remove the effect of negative values as well as to keep it differentiable. So we square it. So f hat x minus E of f hat x, the whole square. And finally, we find the mean of this squared error or squared differences. So we again find the mean using the E operator. So E of this entire thing. So this gives us the variance. Substituting the values, we get the variance as 0.109. That means the predictions are stable across different models. The variance amongst the models, amongst the different models of linear regression is low, but bias is quite high. Variance is low. Okay. Now, sales don't actually linearly increase with temperature. Ground reality is the real pattern might be something more complicated. The real pattern might be, let's say, quadratic. So, for every degree increase in temperature, the footfall increases quadratically. Okay. So, let's say the model, for example, for simplicity, it is, let's say, y equal to x minus 27 square divided by 5, where 27 is like the ambient room temperature. And as the temperature increases above 27, footfall increases quadratically. Okay. The model that we fit, f hat x, was ax plus b. Now, ax plus b is too simple a model for modeling the actual data. So, if our model is simpler than the real pattern, it is called as underfitting. Underfitting is indicated by high bias or high error in the data. Okay. I hope the concept of bias, variance, and this small introduction to underfitting was clear to you.